are going to talk about some simple organic compounds. And kind of like we talked about yesterday, there are some concepts that you guys need to all remember about this. And some of this is going to be repeat for you. But we're going to look at organic chemistry, which is basically just the study of carbon-containing compounds. Typically, we think of organic chemistry as being composed of or being what composes living matter, right? Your living matter is composed of organic compounds. However, there's also some compounds that are considered organic which do not exist in nature. Those are created by man, so they're synthetic compounds that are considered organic. Also, even things like carbon dioxide, they've got carbon in there. So for the most part, we consider those organic compounds, anything that has carbon in it. Like we learned yesterday, carbon always has 4 covalent bonds. It's also unusual because it has that unique ability to bond to itself. So you can get these big long chains of carbon known as catenation. We can look at some differences between inorganic and organic compounds. With inorganic, for the most part, if you heat them up, they're not going to change too terribly. You know, you're going to get some reactions sometimes, but for the most part, if you heat up an inorganic compound, it's not going to change. Inorganic means it's composed of non-living matter. It is more likely to dissolve in water than organic compounds are. And that's mainly because inorganic compounds, for the most part, are ionic bonds. We also get some polar covalent bonds in there as well, but you're going to have things that dissolve in water. They are not flammable. In fact, what we'll learn next semester is that another word for an ionic bond or an ionic compound is a salt. So if you think about just what a salt is, and you guys are used to thinking about table salt, sodium chloride, but it is not going to be flammable. And then also with our inorganic compounds, the atoms do not tend to bond to the same element. The elements don't bond together. Instead, they bond to different elements. Now with organic compounds, again, this is mainly from living matter, but you can get some things that are synthesized. Most decompose or burn when heated. We will see when we start talking about reactions that those are combustion reactions. When you take a hydrocarbon, expose it to oxygen, and give it enough energy, and it burns in air. It's made of chains or rings of carbon bonded to other carbons with 4 covalent bonds. We've said that quite a few times. Most do not dissolve in water, right? So you're not going to see, on most of these, you're not going to see these poles on them. You're not going to see positive and negative sides to them. Many organic compounds are flammable, like we said, combustion reactions. You also have quite a few that are poisonous. And because of the catenation, because of its ability to bond to itself, you get many more organic compounds than you do inorganic compounds, many more out there. Okay, so the simple organic compounds that we're going to look at are known as, they're hydrocarbons, and you can probably look at this and see why they're considered hydrocarbons. We're just going to look at our simple alkanes, alkenes, and alkynes, and then we're going to throw one more on there. And really we're looking at something known as organic nomenclature. We're thinking about a naming system that we're going to be using with these guys. So just like the vowel sounds, A, E, I, when you start saying your vowels, that's how you look at it when you're doing your alkanes, alkenes, alkynes, and it tells us something about the number of bonds that there are. Anes, enes, ines, single, double, and triple bonds is what we're going to end up seeing. And starting with our alkanes, what we see is that these are composed only of single bonds, no double bonds at all. They're just all single bonds. Because of that, they're known as saturated hydrocarbons. All of those hydrogens are wrapped around each of those carbons. You don't have any extra bonds in there. It's all just hydrogens. Our general formula is going to be CnH2n plus 2. I'm going to come back to that here in just a second and show you how we use that. But whenever we go about a naming system with these, we really just have to think about some prefixes. And these prefixes are going to tell us something about the number of carbons in that compound. So starting off, we have meth, eth, prop, bute. That tells us we have 1, 2, 3, and 4 carbons in those compounds. After that, you start using a more familiar system, a Greek or Latin prefix is used. So you guys have all, we'll write these down. You're probably familiar with these already though. So if there are 5 carbons in this compound, we're going to use the prefix pent. If there are 6 carbons, you are going to use the prefix hex. If there are 7 carbons, you are going to use the prefix hept. Now I know that sometimes you see the prefix sept. That's not what's used on this one, it's hept. For 8 carbons, you are going to use the prefix oct. For 9, known. 10 is dec. Okay, so now that we have those prefixes all listed, what we do with those is we just tack on that ending of ane, and that tells us it's single bonded. It's an alkane. So again, tells us our number of carbons and that they're all single bonded. Let's see what else we have here. Now, when we represent these things, there's a couple different ways we can show this. We can show it with a structural formula, and that's some of the stuff that you guys were doing last night on your homework. So I'm going to make sure we know which one of these. This is a structural formula where you have those carbons and those hydrogens, and you're just showing those bonds in between. You can also represent it in a condensed structural formula. This one's a little bit easier to type when you're typing it into a document, but it just doesn't show the bonds, but you can look at the condensed structural formula and imagine where those bonds are. For example, we have CH3, so here's our C with our 3 H's bonded to it. Then you have CH2, so here's our C with our 2 H's bonded to it. And then again, CH3, there's your C with your 3 H's bonded to it. Both of those things are showing the exact same thing. It's just a chain of carbons, nothing fancy is going on with them, so they tell us the same thing. I want to make sure you guys understand some terminology here. And if we were to ask what is the molecular formula, all you have to do is count up your carbons and hydrogens. So I'd look at that and say I have 3 carbons, C3, H, well, you got 8 hydrogens in each case, and you can count both of those and see it's exactly the same thing. So that is a molecular formula. The others are structural formulas or condensed structural formulas. So now I'm going to go back to this guy right up here. We looked at this as being our formula for alkanes. In this example that I just looked at, C3H8, that makes sense. If you have N equals 3, your H is going to be 2 times that 3 gives you 6, plus 2 more gives you 8. So that's what you've got in this case. You're going to see that is the formula that is used for all of your alkanes. And in this case, you guys know what the name of this is? What is it? Propane. Propane, thank you. That's what you use in your grills to make your burgers. So that's our example, first example that we have there for alkanes. All right, as far as these structural formulas go, and these compounds go in general, there are some things known as structural isomers. I am not going to necessarily ask you about those. I just want to show you that what we're going to be working with are just straight chains. We've really simplified this from years past. We used to get a lot more involved in organic nomenclature and get all these branching groups that were involved with it. But now it's simplified. So if I look at this one example that I have here, I've got 1, 2, 3, 4, 5 carbons. So that's pent. I notice that they're all single bonded, so that's ane, pentane. That's it. That's all I have to write. It's a pentane. Now notice over here, I still have 5 carbons, but my longest chain, I've got 4 carbons there. This guy just happens to be tacked onto this carbon in place of a hydrogen, and that's mentioned here. It's known as a substituent group, but what I want to make sure that you guys understand is that naming these branched organic compounds, we're not going to go in depth in that at all. We're not going to address that. So it goes beyond the scope of this class. So maybe you might want to write yourself a note that this is, you are not responsible for naming. So all you need to worry about are just your straight chained alkanes, alkenes, alkynes. Here's something that's interesting for us. When we look at molecular mass, we notice that as that molecular mass increases, the mass of that compound increases, so does the boiling point. So think about what that means. If I were to ask you, which one at just standard pressures and temperatures, which one would you expect to exist as a gas? Methane or octane? Which one would exist as a gas? What do you think? Methane. In fact, that's what's coming out of the jets back there in our lab. Methane exists as a gas because it has a much lower boiling point. It's already existing as a gas. Whereas octane, which goes into your car, it's as a liquid. So in order to get it to turn up into a gas, I have to give it a lot more energy to be able to make it turn into a gas, to break those forces holding it together. Another thing that's kind of important here is that what we see is that these alkanes are soluble in nonpolar solvents. Now, I say this is important. This is really more important for next unit, but I think you guys can handle this whole idea. If you were to look at this compound right here, you could look at that and say, well, that alkane, all of these alkanes, there's no positive end and negative end to that molecule. It's all pretty much the same. No positives and negatives, no poles to it. So this happens to be nonpolar. Well, it's going to be soluble in nonpolar solvents and nonpolar solvents or compounds, because what we end up seeing, maybe you just want to write this down, like dissolves like. Again, this is really more of a topic for next unit, but I just think that this is a good example for us to look at and be able to see why that is, that there are no positive and negative sides here. So if like dissolves like, you would put it into another substance that doesn't have any positives and negatives, it will dissolve. If you put it in something like water, well, that has some positives and negatives, so it's not going to dissolve in water because like dissolves like. All right, that's pretty much it for our alkanes. Now that takes us to our alkenes. And with an alkene, there is just going to be a double bond in there. Anes are single, enes are double bonds. But of course, you can't have double bonds all the way through. There's no way that your carbons could hold that many electrons with hydrogens and such as well. So this is just going to be a double bond that exists between two of the carbons somewhere. If it's not an alkane, it is considered unsaturated. In other words, if it's only single bonds, it's saturated. If it has anything beyond single bonds, it's considered an unsaturated hydrocarbon. Our alkenes end in the ene ending, and notice now that our formula has changed. I don't know why I just did that. To CnH2n. So we didn't add that +2 anymore because those two electrons from our hydrogens are tied up in a double bond now. So that's our new formula. And we're going to have the same exact system for naming these, so same prefixes. Let's scratch this off because that is just a function of Word thinking it's smarter than me, that numbering system. But I want to scratch that off because that's not telling us our number of carbons. Think about it with number of carbons. Ooh, in fact, it looks like I made a mistake. I forgot methene. Should I have methene up there? Good, okay. There's no way you can have a methene, one carbon. You can't have a double bond if all you have is one carbon. So there should not be a methene there. Again, you're using the same prefixes. Here's the biggie on how you go about naming your alkenes. You need to go ahead and number the longest chain containing the double bond, which we're only working with single chained carbons, so that's going to be the case. It's going to contain the double bond. You're going to need to number it so that the lowest position number is assigned to the carbon atom with which the bond is attached, the first carbon atom. So you want that double bond to be the lowest number possible is what you're trying to do. So for example, you guys have this, on yours you have them numbered, but let's look at this as being 1, 2, 3, 4, and 5. Well, if we numbered it from this direction, we're counting our carbons. I see that my my double bond is located on that third carbon. That's the first time I hit that double bond is on that third carbon. If I number it from the opposite direction, 1, 2, 3, 4, 5, I actually hit that double bond on the second carbon. That is the lowest position, the lowest number. That's always what I want, is to find that double bond that's on that lowest numbered carbon. So this is the correct way to do it. This is incorrect. When I name this, I'm going to look at this and say, oh, I've got 5 carbons. That's pent. Oh, there's a double bond in there. That's going to be an ene, pentene. Make sure when I'm trying to grade something, make sure I can see the difference between an A and an E. If I can't tell the difference, then I can't give you credit for it. But this is going to be a pentene. Then the last thing you need to do is tell where the position of that double bond is. And the way we do that is just with a number in front. You do a number and then a dash and then the word pentene. So again, I see that I get that carbon off, the double bond off that second carbon. So it's going to be a 2-pentene. All right? All good? So we move on to our alkynes, and just like you would think, we've got our triple bond going on here, and our ending is going to be an -ine. All right, so with our alkynes, we've got a triple bond, and again, it's unsaturated. Notice that our general formula, again, we have an extra bond in this case, so our formula is going to be CnH2n. Now we have to subtract another pair of electrons, right? So it's going to be 2n minus 2, because you've got those electrons that are tied up in a double bond or a triple bond now. Again, we're going to use our same prefixes, so I'm going to get rid of this numbering system. You can't have a methine, not possible to have a triple bond if you only have one carbon. So we continue with these. Not all of the prefixes are written down. Something I do want you to notice though here, in this first one, ethine, you only have 2 carbons. The only possible place for a triple bond is between those 2 carbons. Here in the second one, propyne, I've got 3 carbons. I've got my triple bond between those guys, so if I were to try and put a number with that, what would you call it? What type of propyne is it? 1. It's a 1 propyne. Well, if I put my triple bond on this side instead, it would still be a 1 propyne. So because of that, because there's no other possible way to phrase that, you do not write the 1 in front of it. You just write it as propyne, just like you just write this as ethine. However, when you start getting to more complicated ones that have more carbons in there, for example, if we were to do a bute, there are my 4 carbons. So let's say, maybe I'll put it on this side. Let's say I've got a triple bond on this side. Before we even name it, let's go ahead and finish up with our hydrogens. On a quiz or a test and a homework, you need to write all your hydrogens in there. I'm lazy. I'm going to do tick marks right now, but I'm special. Y'all can't do that. You have to write your hydrogens in there. So make sure you know how many hydrogens to add. How many do I add to this carbon? None, because he's got his 4 bonds. This guy just needs 1 more hydrogen. So in this case, who wants to try naming this? Anybody? You know you want to. Somebody. What is it? Okay, what kind of butane? 1. It is a 1. Oops, I can't write. That says 1-butene is what that says. Because that triple bond right here is on carbon number 1. I would just start writing from that side. However, what if we had something like that and we had our triple bond here? In this case, we've got our hydrogens coming off of there. I don't need anything there. But we've got that situation. What are you going to name this? It's a 2-butene. Good. All right, so I just wanted to stress that and make sure you guys understand the numbering system, that you need to go ahead and do that. All right, last little bit now. We're going to look at something known as cyclic hydrocarbons. You did this on your homework, but you didn't know the names for them. So we had to tell you, hey, on this example, put it in a ring. So that's what you saw. In a cyclic hydrocarbon, you're going to take the two ends and join them together to form that ring, and we're calling it a ring. If you only have 3, it looks like a triangle. If you have 4, it looks like a square, but you're attaching them all in a ring. This can work with alkanes, alkenes, alkynes, but remember, they're cyclic alkanes, cyclic alkynes, and cyclic alkenes, so they're not going to have that same general formula. Don't think that it'll be the same thing because the two carbons are attached, so that takes that away. All right, notice right here that everything that we have listed here is a cycloalkane. The way you name these, by the way, is just you add that cyclo prefix before your root word. So these are all cycloalkanes. What if I were to draw something like, let's do that. And again, we've got our, here I'm just going to have 1 hydrogen. Here I have 1 hydrogen. I'm going to have 2 hydrogens attached to each of these guys. So now this is a little bit different than what we have above. What are you going to name this? Exactly. So in this case, specifically, it's going to be cyclobutene. And going back to that whole numbering idea, you get to choose the number. Well, you are automatically always choosing this to be the lowest number, so it's always going to be a 1. Therefore, you do not write it because there is no other option. It's got to be a 1. So a cyclobutene says it all. That's all you would write on that. All right, nicely done, guys.